In this video, we'll continue our introduction to the derivative. This is the second of two videos for this section, 3.1, introducing the derivative. I'm going to look at problem number 40, which applies the definition of the derivative of a function at a point to a specific problem, because the problem says to start by finding f prime of a. Find the first derivative at a point A. We're given for number 40 that f of x equals the square root of 3x. And we're given for number 40 that a equals 12. So you can see that f of x is the square root of 3x. If we wanted to write out an expression for f of a, it would be the square root of 3a. When a is 12, that would give us the square root of 3 times 12, or the square root of 36. And the square root of 36 is 6. If I wanted to find an expression for f of a plus h, that means to go to our function and replace this x with a plus h. And when I replace the x with a plus h, I would get the square root of 3 times a plus h, or in this case, we're given that a is 12. So if I replace a with 12, f of 12 plus h will be the square root of 36 plus 3h. So let's look at this definition of a derivative at a point, and let's do the calculation. The first derivative at the point a, where let's say where a equals 12, is going to be the limit as h approaches 0 of f of 12 plus h that's f of a plus h with a equal to 12, so f of 12 plus h minus f of a, so f of 12, which we found was 6, all over h. If I wanted to evaluate this limit, I can't replace the h with 0 because that would give us 0 in the denominator. Doesn't work. So I need to use a tool from chapter 2 for evaluating limits, which is to multiply by the conjugate. So do you recall that I could multiply by 1 in the form of square root of 36 plus 3h plus 6 over the square root of 36 plus h plus 6. Really, this is just a big 1, right? This is just a 1. I'm multiplying by 1. But I'm using 1 in the form of the conjugate of the square root of 36 plus 3h minus 6. Why am I doing that? Go back to your basic algebra and remember this difference of two squares. What happens if I multiplied a plus b times its conjugate, a minus b? I would get a squared minus b squared. So when I multiply this numerator times the numerator, I'm going to get the first term squared minus the second term squared, because I'm going to get the difference of two squares. So I'm going to get the square root of 36 plus 3h squared minus 6 squared. And this is now going to all be over h times square root of 36 plus 3h plus 6. When I simplify this, the square root squared, or in other words, the square of the square root, is going to give us the radicand. The radicand is a way that we can describe what's in the radical. So the square of a square root, we're just going to get that back. So we're going to get the 36 plus 3h minus 6 squared all over h times the square root of 36 plus 3h, that's all in the radical, plus 6. Make sure you're clear that the radicand is the whole 36 plus 3h. The 6 is outside that radicand. You see what's going to happen next is the 36 minus 36 will cancel, and then the h over h will reduce. It reduces to 1 because h over h is 1. And what am I left with? I've got 3 over the square root of 36 plus 3h plus 6. And when I use the direct substitution, I'm neglected to keep this is the limit, right? Bad form there, not to continue writing that. But the limit, as h approaches 0, of this is going to be now evaluated by replacing the h with 0. So I'm going to have 3 over the square root of 36 times 0 plus 6, or 3 over 6 plus 6. I can reduce 3 over 12 to get 1/4, and that is, in fact, the derivative. So I've found the f prime of 12 is equal to 1/4. Part 1, or part A rather, is done. We got that the first derivative at 12 is equal to 1/4. Part B is just the algebra piece now. Part B says determine the equation of the line that's tangent to the function f at this point a f of a. So for our problem, we've got a slope of our tangent line is defined as the derivative at the point, so our slope is 1/4, and we have this point a f of a, square root of 36, which was, let me rewrite it just to make sure we've got everyone. F of 12 would be the square root of 3 times 12 is 6. So we've got the point a equals 12, f of a equals 6. And if I want to find the equation of this line, you could use y equals mx plus b, or you could use y minus y1 equals m times x minus x1. Either one works just as well. I'm going to go ahead and do both just to make sure everyone's comfortable with one or the other. For y equals mx plus b, what I like about this is now I don't have to remember another equation, but I'm going to replace y with 6, m with 1/4, x with 12, find that b equals 3. So y equals m x plus b, or in other words, y equals 1/4 x plus 3. So what I did here was I had to use y equals mx plus b, inserted our point, x equals, x was supposed to equal, oh yeah, that is right, x is the 12, I thought I had those reversed. X equals 12, y equals 6, plus b, and I can use this to find the intercept b, which equal 3. Once I had b equal to 3, I could go in and put the m and the b. The other format, and these are equal, either one will work, y minus y1. So our y is going to be 6 equals m x minus x1. So x minus 12. One-fourth of 12 is 3. Plus 6 gives me plus 3. So you see how we get the same answer either way. You could solve this with either of those two. Just use whichever one is most comfortable for you. Let's try one last example. This one only has finding the derivative, and then we're done with the problem. It's not asking us to then find slope. So we're going to use that f prime of a is defined as the limit as the distance between x and a gets closer to 0 of f of a plus h minus f of a all over h. I'm recommending that you write this definition each time you're going to use it. If you do that, you'll get more and more accustomed to it in such a way that it'll become more and more obvious what it is that we're actually doing with finding the slope between these 2 points. Doing the substitution, if we have f of the radius is pi times radius squared, then f of a would be pi times a squared, and f of 3 would be pi times 3 squared, or 9 pi. F of a plus h would be pi times the radius squared, and if we're using a plus h for the radius, it would look like this. If we're going to let a equal 3, looks like we would get pi times 3 squared plus 2 times 3h plus h squared, all times the pi. Let me work that out for you. The derivative at a is going to be the limit as h approaches 0 of f of 3 plus h squared minus f of 3 all over h. If I multiply 3 plus h times itself, I use the factoring pattern. So the square of a sum is equal to the first term squared plus 2 times the product of the two terms plus the second term squared. You could also, if you're not convinced of that, try foiling it and you'd get the same thing. But what we have is the limit as h approaches 0 of pi times 9 plus 6h plus h squared minus 9 pi all over h. When I distribute the pi, I get 9 pi times 6h pi times h squared pi. So the 9 pi minus 9 pi cancels out, and I have the limit as h approaches 0 of 6h pi plus h squared pi all over h. I could factor out the h. or I should say factor out one of the h's. 6 pi h divided by h is 6 pi. Pi h squared divided by h is pi h, all divided by h. Do you see why I factored it out? So that I could reduce that, because h over h is 1. And now I can replace the h with 0 and evaluate that the limit as h approaches 0 of 6 pi plus pi h is going to be 6 pi plus pi times 0, or just 6 pi. And that's it. Well, that wraps up the examples I have. If you have questions about these examples, please don't hesitate to contact me or ask when we meet for class. And I hope that these examples will help you through the practice problems in the homework.